Now that we know about the inverse sine function, the arcsine function, and we know about its graph and where the restrictions on the domain come from for sine so that we can talk about inverse sine, let's do the same thing for cosine. I'm going to start though by drawing a quick graph of the sine function and use that to remind us of where the domain restrictions come from for sine so that we can apply that to cosine. Here's a graph of one cycle of the sine function. We need to remember that this graph continues in both directions beyond the single first positive cycle that we see sort of stereotypically defining what the sine function looks like. In order to be considered a function, a graph has to pass the vertical line test. This graph will pass the vertical line test, but its inverse will not, at least not for all of the function. To pass the vertical line test, a function's inverse has to pass the horizontal line test. This function won't do that unless we restrict the domain. At one point, we talked about restricting the domain to the range of values pi over 2 to 3 pi over 2. That would mean that this function passes the horizontal line test, which means its inverse would pass the vertical line test, making that inverse a function. But this isn't a convenient range of values for us. So instead of this range of values, pi over 2 to 3 pi over 2, we'll use negative pi over 2 to positive pi over 2. It's important to note that the sine function in and of itself does not need to have its domain restricted. The domain of sine is all real numbers. I can plug in any number, anywhere on the x-axis, anywhere on the real number line, positive or negative, and I'll be able to find the sine of that number. The problem arises when I want to talk about the inverse of sine. If the inverse sine is going to be a function, then the inverse of that, the sine function, must be a one-to-one function. It must pass not just the vertical line test, but also the horizontal line test. This piece of the sine function does. Moreover, it's the longest piece, or any stretch like that would do. It's the longest piece that's one-to-one that passes the horizontal line test as well. And it's conveniently located sort of symmetrically around the origin. This is the graph of y equals the sine of x. Let's also graph y equals the cosine of x on this other set of axes. And then let's take a look at its horizontal and vertical line test. Again, the cosine continues in both directions. And this graph will pass the vertical line test, but it will not pass the horizontal line test. So I need to restrict its domain if I want to be able to talk about the cosine, the Arccosine or the cosine inverse. So our job now is to figure out which piece of this graph, the longest piece we can find, will also pass the horizontal line test. We can't use the same range of values that we did for sine because for negative pi over 2 to pi over 2, that piece of the cosine graph will not pass the horizontal line. A piece that will is the part that starts at 0 and goes to pi. Now, if we'd wanted to, we could have chosen pi to 2 pi, or we could have chosen negative pi to 0. But we use 0 to pi primarily because it's convenient, it's all positive, and because we can't use the same range as we did for sine anyway, we might as well choose the next possible longest stretch of values that we can use with cosine in order to be able to talk about its inverse. All right, let's talk about the graphs of arcsine and arccosine. I'll start with the notation, actually. We've already talked about y equals sine inverse can be written as y equals arcsine. It just has the letters ARC in front of it. The same is true of cosine. I can either write cosine inverse or I can write arccosine. ARC come in front of the normal COS. We've already graphed arcsine, although we did it a slightly different way. So let's go ahead and use this opportunity to graph arcsine and arccosine on the same screen. Arcsine, because sine has values that go through 0, 0, pi over 2, 1, pi, 0, and so on, but we only want the values for arcsine, we only want the values in this highlighted region. And also remember that the points for the inverse graph will come from reversing the x and y coordinates. So this point right here, for example, is pi over 2 comma 1. But to graph that in the inverse, I'm going to graph negative pi over 2 comma 1 becomes 1 comma pi over 2. 0, 0 stays where it is. And negative pi over 2 comma negative 1 becomes negative 1 comma negative pi over 2. Now this graph from 0, actually let's start at pi over 2 comma 1. Pi over 2 comma 1 comes down through 0, 0, but it does so by getting closer to the y-axis first. It kind of comes out almost as though it's going towards the y-axis, and then it bends down. So in the case of the arcsine, I want it to come towards the x-axis before it starts to bend down. So it curves that way. We could take another point on here to verify. Let's do pi over 4 root 2 over 2, which is about 0.71, and that becomes 0.71 pi over 2. So that point is going to go 0.7 pi over 4. Sorry, not pi over 2, pi over 4. 0.7. It comes out farther here before it goes up to the halfway mark between 0 and pi over 2. So here's pi over 4. And I'm going to go all the way out to 0.7 before I get there. If I went to the halfway mark, I'd end up with a point there. So this confirms that I'm bending the right way. All right, let's do the same thing for cosine. Here's the range of values I want to use. Cosine goes through 0, comma 1. So arccosine goes through 1, comma 0. Cosine goes through pi over 2, comma 0. So arccosine is going to go through 0, comma pi over 2. Cosine goes through pi, comma negative 1. So cosine inverse goes through negative 1, comma pi. And then looking at the original graph, cosine goes away from the y-axis quickly and then slowly starts to come down towards the x-axis. So in this case, it's going to come away from the x-axis quickly and then slowly come towards the y-axis. So my bend looks something like this. Now, notice that the domain for sine is all real numbers and the range is negative 1 to 1. The domain for arcsine, the domain for arcsine is negative 1 to 1, and the range is not all real numbers. It's just these values here. So when dealing with arcsine, or when we think we're going to have to deal with sine inverse, we restrict the domain on sine to values for x that are no smaller than negative pi over 2 and no bigger than pi over 2. For cosine, we restrict our domain to 0 to pi. They both have a range of values that's pi wide, but it's a different range of values. Using interval notation, I would get negative pi over 2 in parentheses, comma, pi over 2, not parentheses, square brackets. And for cosine, arccosine, I get 0, comma, pi. And I'm using square brackets here because I'm including the values of negative 1, comma, negative pi over 2. That's this one here. It's that point down there. I can include the value of negative pi over 2 in my domain of sine, my domain for sine, in order to be able to invert it. Because the value that gives me, the x value that gives me that y value, that negative pi over 2 that gives me that negative 1, there's no other value that gives me a negative 1. So I can actually include the pi over 2 in my domain. Same thing with negative pi over 2. Same thing with pi over 2. For cosine, there's no other x value that gives me a 1. So that means there's no other y value that can be traced back to this x value of 1 for cosine inverse. So that means I can include the 0. Same thing with pi. All the way out here at pi, there's no other x value that within this domain, than this restricted domain, that gives me a value of negative 1. That means that for the arccosine graph, I'm never going to be able to track this y value of pi back to anything other than negative 1. That's what makes this a function. So I can include pi in my domain, my restricted domain for cosine, if I want to be able to talk about Arccosine. We want the largest possible range of values available in each case so that we can capture as much of the behavior of the graph as we can when talking about inverses. So if we can include the endpoints, here it's 0 and pi, and here it's negative pi over 2 and pi over 2. If we can include those endpoints, then we do. Okay, the other thing I want to mention on this screen is that in the same way as we had arcsine of some value equals the angle, I'll call it theta for now, arccosine, I left off a C there, arccosine of some value, I'll go ahead and use the same value, equals some other angle. What this one said was, what is the angle? The answer is the angle. The question is, what is that angle whose sine is 1/2? What is the angle that has a sine of 1/2? And the answer is pi over 6. So that means I can replace this theta with pi over 6. The sine of pi over 6 is 1/2. So the arcsine of 1/2 is pi over 6. Remember, x's and y's are reversing roles. That's what inverses do. For the cosine, for the arccosine of 1/2 is an angle. It's the angle whose cosine is 1/2. What is the name of the angle that has a cosine of 1/2? And the answer there is pi over 3. So the arccosine of 1/2 is pi over 3. Also, like sine, I haven't done this for cosine yet. We've restricted the domain for cosine to 0 to pi if we want to talk about arccosine, and that's this range of angle values in here. So we're in quadrants 1 and 2. So as with sine, there are two places where the arccosine of 1/2 exists. Remember that cosine is adjacent over hypotenuse. So if I have an angle like this where that adjacent side is 1 and the hypotenuse is 2. And remember that all ratios are positive in quadrant 1. Only sine and cosecant are positive in quadrant 2. Tangent and cotangent in 3. And cosine and secant in 4. So the other place that the cosine of an angle is positive is down here in quadrant 4. But we're not allowed to play with arccosine in quadrant 4. The other angle would be something that looked like this. That adjacent is still 1. That hypotenuse is 2. My drawing's a little bit off here. So that angle does exist. There is another place that there is an angle whose cosine is 1/2. But we're talking about arccosine as its own function, and it's not a function if we play with it in quadrant 4. So it has to be this angle here in quadrant 1. So pi over 3 is our answer. Right, the next thing to look at is how to compose cosine with arccosine and arccosine with cosine, but I'll do that on the next screen. Okay, we're going to do some evaluation practice down here, but before we do, I want to remind you that when you compose a function and its inverse, or an inverse function and its inverse, which is the original function, you always get x, except that in the case of periodic functions, we've had to restrict the domain on cosine in order to be able to play with arccosine. So our domain restrictions may affect our results here. In other words, the cosine of cosine inverse of x is always going to be x, as long as x is between these two values. So let's talk through what those values could be. If I do a composition, I'm always going to do what's inside first. So I'm going to take the cosine inverse of x, and when I do that, I'm going to be given an angle, right? The cosine inverse of a value is the angle whose cosine is that value. So this is going to spit out an angle. Now that angle, as we now know, is going to have to be between for cosine, it's going to have to be between 0 and pi. But then when I take the cosine of anything between 0 and pi, I end up with values that go all the way from -1 to 1. So if I take the cosine inverse first, and then take the cosine of that value, I'm going to get some number. The cosine of any number is somewhere between -1 and 1. If I take the cosine first, and then take the inverse cosine, then my values end up being between 0 and pi, because that is the restricted domain for cosine when I'm playing with inverse cosine. So I'm going to get x for the answer to both of these, except that x has to be within the range of values -1 to 1 if the composition is in this order, and x has to be within the range of values 0 to pi if the composition is in this order. All right, let's do a couple of examples. I'm actually going to do this one first because taking the cosine of an angle is comfortable and familiar, or at least it should be by now. So let's pick an angle. I'm going to go with 60 pi over 47. I can take the cosine of any angle I want. All I have to do is plug this into cosine and it's going to spit out a value. The question is, do I really need to do all of that? Because I know the cosine inverse of the cosine of a value is just the value, as long as the value is in this range of values here. Is it between 0 and pi? And it's not, right? Pi would be 47 over 47 times pi. I should be doing it with this one in here. 47 over 47 times pi would be pi, 1 times pi. So 60 over 47 pi is too much. How much too much? Well, how much bigger is 60 than 47? Let's do 60 minus 47. 10 minus 7 is 3. 5 minus 4 is 1, so it's 13. This is too big by 13 pi. So I need to figure out where this angle lives, 60 over 47 pi, and find an angle that has the same cosine as this one, depending on its sign. I can figure out what the reference angle is, figure out what the cosine of that is, and then it's that angle that will have to act as my x, giving me this formula here. So let's figure out where 60 over 47 pi is. It doesn't need to be exact. I just need to know that it's somewhere in quadrant 3, right? It's bigger than pi by 13. Well, by 13/47ths, I should say. This is 13/47ths, too big. So I need to find an angle whose cosine is the same as the cosine of this angle right here. Well, this angle right here is 13/47ths pi. Yes, I should put that on there too. And I also want to remember that all students take calculus, and so the cosine that I get when I take the cosine of this angle, it's going to end up being negative. So I have to be, with cosine, I have to be between 0 and pi if I want to talk about arccosine. And I'm going to be taking the arccosine of the value that I come up with here in a minute. I'm going to be taking the arccosine of the answer to this question. So I have to make sure that the answer to this question comes from an angle that's in one of these two quadrants. All right, it's not currently, it's too big. So what would the sign SIGN of the answer be? The sign of the answer to the cosine of this angle would necessarily be negative. Let's do that in pink. Where else would the sign, when I take a cosine of an angle, where else would I get a negative answer? And that is in quadrant 2. So in order to take the cosine of this angle so that I can turn around and take its inverse cosine, I need to be dealing with the angle that has the same cosine and has the same sign, SIGN, but is in a different quadrant. Specifically, it's the one in quadrant 2. Now, if this is 13/47ths too big, then this is 13/47ths. It's 13/47ths back from pi. So now what I need to do is figure out what pi minus 13/47ths pi is. And that's 47/47ths pi minus 13/47ths pi, which is 34/47ths pi. So I can replace 60 over 47. This is really actually not terribly accurate. The way I've got this 13/47ths pi in here, I should have said that it's 13/47ths pi too big. Right? The way I had it before made it look like I could replace this with 13/47ths pi, and that's not true. What I can replace it with is 34/47ths. So let's write that down here. This is equivalent to saying take the cosine inverse of the cosine of 34/47 pi, and that's equal to, now this is less than pi. It's bigger than 0 and less than pi. So now the answer is just that the cosine inverse of the cosine of x is x. So I get 34/47 pi for my answer. It's very tempting when you see these to just write down the answer as 60/47 pi, but it's not, because I can't take the cosine inverse of the answer that I get when I evaluate this 60/47 pi, cosine of 60/47 over 47 pi. I can't take cosine inverse of that because the angle is too big. I have to be in quadrants 1 and 2. All right, let's take a look at this other example. I'm just going to move my scratch work up here for this one. And so far I haven't used this grid. I don't know, wasn't sure why I put that there. I'm not sure why I put that there, but I haven't used it. So, all right, I'm going to do this one now. Now the cosine inverse of a number is the angle whose cosine is this number. So I want the answer to a cosine question here, and I'm going to use -1/2. Okay, the answer here is, again, just the cosine of the cosine inverse of a number is just the number as long as that number falls between -1 and 1. And in this case it does, so we're done, right? I would say that by way of demonstration, I guess I can bring this down here and use it here. By way of demonstration, the cosine, let's do this. The cosine of an angle is negative. This is where I get to deal with cosine inverses. The cosine of an angle is negative. Cosine is adjacent over hypotenuse. And so cosine is positive here and here and negative in quadrants 2 and 3. So I want an angle in either quadrant 2 or quadrant 3, because then my opposite is going to be negative, so that'll be -1 over hypotenuse, which will be 2. Okay, except that I can't use this one because I can't take the arccosine of an angle in quadrant 3. I'm not allowed to. I have to play with those in quadrants 1 and 2. So I have to use this angle here, but what is the cosine of this angle? Well, it's -1/2, right? This value is between -1 and 1, and so the answer is just the x, the input that I have here. All right, just about the only thing left to talk about now is what happens if you get asked a question like this. Well, that's a calculator question. I could go figure out what -11/100 was and find the triangle that satisfies that. It would actually be one of these two quadrants. But I'm not doing a composition here. I'm just finding the arccosine. So if I want to know what the arccosine of some value is, and that's not a nice angle, right? It's not a nice, like it's not square root of 3/2. It's not 0 or 1. It's not a half or -1/2, right? It's not any of those familiar values. I'm going to have to use my calculator. So here again, I'm going to go second cosine, and that gives me the cosine inverse function. And then it opens a set of parentheses for me. I'm going to type in -0.11, close the parentheses, and hit the enter button. And that'll give me the answer. So that's pretty much it for arccosine. That was a lot shorter. The next one we're going to talk about is arctangent.